Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is shortest distance after row addition queries 1. Let's go to LeetCode. So in this problem, you are given an integer n and a 2D integer array called queries. There are n cities numbered from 0 to n minus 1. Initially, there is an undirected road from city I to its next city, which is I plus 1 for all 0 to n minus 1 cities. Now this queries at the ith position represents a pair that holds u and v, which basically tells us that there now you can add an edge from u to v. So it's like a directed graph. Or is it directed? No, it's actually undirectional. So there isn't a path from u to v, so there is a path from v to u as well. Now after each query, you need to find the length of the shortest path from city 0 to city n minus 1. Return an array answer where for each I in the range 0 to queries length minus 1, answer I is the length of the shortest path from city 0 to city n minus 1 after processing the first I plus 1 query. So basically they have in the first example, they in these pictures, they have shown really nicely how the answer is calculated. So you are given this initial graph. Let me just take you to basically iPad here. So we are given n, which represents the number of nodes. So for us it's 5 in the first example, and then we are given queries. Right, we are given queries. So basically this n represents this particular graph right here, this graph right here, and now we are given these queries, and this query holds this value, first pair. So at the end of the day, we will be returning answer, and this answer is going to be of the same length as queries, but how you calculate answer is pretty interesting. Now your answer will be of same length as queries. I'm going like really slow, but that's because it's a really interesting problem. I don't know what I'm talking about. So what's really happening is, the reason I have drawn three graphs right here. So this is the original graph. This is the original graph. Now each query represents an addition of an edge from basically this right here. So this, when I'm saying that right now at query at the 0th position right here, 2 and 4, there is a path that I'm adding. So in this graph right now, the shortest path in this original graph, the shortest path from 0 to n minus 1, which is 5 minus 1, 4, right here is 1, 2, 3, and 4. So you have to take 4 edges. That is the shortest path in the original graph, right? But the problem is saying that at queries ith position, it's giving us a u and v value, and there is a path that you can add now from u to v. So I will add an extra edge from u, which is 2 to 4, like this. So now there is another edge going from 2 to 4, and that's where I will be calculating my answer. So what is the shortest path? Shortest path from 0 to n minus 1, which is 4. So in this case now it's going to be, I can take this path. So 1, 2, and then directly from here 3. So right now it's going to be 3, right? So I will have my shortest path now for after adding this query 3. So I will add 3 to my answer. Then for the second query, this value right here, I will add this extra path to basically my after addition of this particular path. So this path has already been added. I will add this. Now there is a path from 0 to 2 that I can add. So there is a path from 0 to 2. This is the second path that I'm adding to the query 0 that I've already added. So now if I am trying to find the shortest path from 0 to 4, that will be, I will take path, because I don't have to take this longer path, right? Not 2 edges. I can take direct edge to 2, and from 2 a direct edge to 4. So now the path would be 2. So in my answer I will have for query 2, after adding this edge at query 2 to my graph, now my answer would be 2. So shortest path from 0 to n minus would be 2 now. How about if I add this third query to my graph now? So I will be adding this. So if I'm adding this, that means these two edge are already part of it now. These two are already part of it now. And then I'm adding 0 to 4. So 0 to 4 would be this. I'm adding this. Now the shortest path from 0 to 4 would be just 1, because I don't have to take any of this path or this path or this path. I can just directly jump from 0 to 4. So that would be just direct one edge that I'm taking. So my answer here would be 1. My answer would be 1. So you can see, like, this is a very brute force way of finding the shortest path, that you actually traverse through the graph after adding all these queries. So if for each query you add to your graph, so initially we will create our graph adjacency list. So step 1 would be, so I will just move this entire thing and note down our steps right here. So for this, our step 1 would be for each query. So basically if I write my approach, it would be for each query, after it's added to our graph adjacency list, then run BFS to find shortest path from 0 to n minus 1. That sums up. And we already know how to write a BFS. We already know how to create a graph adjacency list, right? We have done it so many times. Now this will be of this solution would be of time complexity big of n, if that's the initial number of nodes. In this case, let's say it's 5, and then there are q number of queries. So that will be the, for this n is basically it's the BFS. Our BFS will be taking n number of big of n time complexity to run to visit all the nodes, and then q is the number of queries that are given to us. All right, and for space we are actually not really utilizing any space, and or maybe we will be utilizing the visited set. So that will be big of n, or the number of vertices. So I'm just I think that would be it. Now we can move on to basically writing the code. I don't think we really need to. It's an easy problem, and that is the brute force solution, and that is also I would say the optimal solution as well. Because you don't really need to dive deep into, but I'm sure like you can optimize a few things, but I think this is good enough for this problem. So as I said, we will create the graph adjacency list. Initially it's going to be a default. We have to write default. We can just say, we can say default dict of type list. Now I'm going to visit for I'm gonna say for each node. So for I in range n is already calculated. Now what I'm going to do is I will go actually up till n minus 1, so such that like it will go actually up to n minus 1 originally, but now it will go up to n minus 2, so that I can add to my graph So graph at ith dot append to its list, I will be adding its next value as neighbor. All right. So as I said, like there is an edge going from I to I plus 1. So I can go to I plus 1 because I plus 1 is the neighbor of I. All right. Now for each query that is given to us, it will be u and v in my queries. So in my queries, and what I'll be doing is basically I will be running a BFS on from u to v. So I'm trying to like I'm sorry, I'm running a BFS from 0 to n minus 1, but after adding this u and v. So into my graph, what I'll do is at u I will be append this v to my u. All right. Once I'm done doing that, then I can create my answer variable here. So answer, an empty array, and this empty, and I can just basically run a BFS and append that value to answer. So to my answer dot append whatever BFS return, BFS will return me an answer. And to this BFS I don't really have to give anything. Do I have to? Yeah, I don't have to give anything, because always the source is 0 and destination is n minus 1. So I can just like simply just leave it. This function might not even like get anything, but actually I think it would be better if I just like give this a empty visited set, because for each BFS that is going to be different, right? And then finally I can just return my answer. So it's the time where basically implement BFS, not DFS, my bad. This will be taking a visited set, right? Visited set. Now to my queue, I can add dq. I can add this initial node, which is 0, and then I will add this to my visited set 0. And then one more thing is that I am going to add the count of basically the which is more like level or length, you know, or I can say this this level. So initially this level, should this be part of I guess this doesn't have to be part of the this doesn't have to be part of the parameters, because I can actually just declare it right here, and initially it will start with 0. I think it should start with 0, and then once I actually start exploring the first first level node, so first neighbors of basically current u, which is this, that's when I can increment it. So I will just have it marked, so I can call it level. Initially level is 0, and then I can say for neighbor, so a neighbor in graph for what. But before that I will have my while loop. So while q is not empty, and I will take out this u, which is the source, which is 0. Initially it's 0, it will later keep changing. So now I will pop out, so q dot pop left, it will give me the u, and actually this u will give me this right here. And yeah, so by the way here, if this neighbor is actually equals to what, destination, which is n minus 1, that's when I can just return, and sorry, my bad, here I can just increment the level here, right, because I'm entering into the next level. 1. So I can just return the level. All right, maybe when I was like on 0, I was exploring 0, and from 0 its neighbors is actually, one of the neighbor is n-1. So I've found my shortest path, which is this level I incremented it to 1 now. So this I will return. But if this is actually not equal to that, then I would want to explore it. But I would only explore it if it is, if this neighbor not in visited, that's when I will only add it to my queue. Right, I will add it to my queue, and then also I will mark this visited. Dot add, and basically neighbor. I bet it's neighbor, and that is it. Well, they kind of said in the problem that like it's guaranteed that we will actually find the shortest path, so that will always be there. But to be on the safe side, I will actually return this level, because just in case. So now I guess that will be all. Now let me zoom out. I hope you can see the entire code. Okay, so now here's the entire code. So here actually I think we have done just a little mistake, which is like it's not giving us u, it's actually giving us, it's not just giving me, it's not supposed to give me just one node. So rather than this, what I'll do is I'll have this 0 added over here, and then I'll transfer whatever queue provides me to into a small queue, and then for everything in my small queue, I will be running for all those neighbors. So for actually node in queue, that will be giving me basically this node. I wouldn't have to actually now pop. I will actually just like, for this node I will be visiting all its neighbors, right? So I think that will be it, and I guess at this point it will be okay to increment the level right here. And let's try this now. Awesome. Yeah, it's been a while that I've written the BFS. Anyway, it was easy to miss. Alright, so this is the entire code. Now we already talked about the time complexity. Time complexity is big of n into q, and space complexity is going to be big of n, because we are doing it for all, like visited set can at max store all the nodes, right? Alright, so let's go back to AlgoYogi and mark this problem solved. See you guys later in the next problem.